The following program is brought to you by Caltech.
Good evening. My name is Tom Sofer, and I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. This is one of the best parts of my job, being able to introduce the speakers at these Watson lectures that are from our division. Before I do that, I want to remind you the next lecture in this series will be on November 6th, and will be by Axel Scherer, the Bernard Netjes Professor of Physics, Electrical Engineering and Applied Physics, and the title will be From Lab on a Chip to Lab in the Body, the Role of Nanotechnology in the Miniaturization of Medical Diagnostic Tools. So, having taken care of that piece of business, it's my pleasure to introduce tonight's speaker, Richard Ellis, the Steele Professor of Astronomy. Richard received his undergraduate education at the University of London and his graduate degree from Oxford University. After a series of appointments in England, culminating in being the Plumian Professor of Astronomy and the Director of the Institute for Astronomy at Cambridge University, he joined the Caltech faculty in 1999. Richard is involved in research projects ranging from the study of the structure and evolution of the universe to the nature of dark energy. In all of these, he's one of the world's leaders. He's a major user of the most sought-after astronomical facilities, the Keck telescopes, the Subaru telescope, the Hubble Space Telescope, among many such observatories. As of August of this year, he has published 379 refereed articles and 533 articles in total. This is an extraordinary output even by Caltech standards. Richard has received many awards for his achievements. Most notably, he shared the Cosmology Prize of the Gruber Foundation for his work with the supernova cosmology and high redshift supernova search teams. He's a fellow of the Royal Astronomical Society and the recipient of the gold medal of the Royal Astronomical Society. I think his most notable award is he's a commander of the British Empire, making him a peer of Michael Caine, Elton John, Stephen Hawking, and Catherine Zeta-Jones. He outranks David Beckham, J.K. Rawlings, and of course, John, Paul, Ringo, and George. And he also outranks the chairman of the PMA division. In the last few years, Richard has extensively used the Keck telescopes and the Hubble Space Telescope to study the youngest galaxies at the time when they are just lighting up. In this endeavor, he is described as an observational cosmologist. Many years ago, I was watching a television program, and these observational cosmologists were referred to as the lords of creation. As one of the major lords, he will tell us about his work tonight in his talk appropriately titled, Let There Be Light. After his talk, he will take informal questions at the podium. And with that, let me introduce Richard Ellis.
Thank you very much, Tom, for that introduction. Good evening, everybody. I'm going to try to describe tonight an adventure that takes us back to when the universe was very, very young. And time travel is something, I think there's always been a dream of time travel. Imagine that we could go back and meet William Shakespeare, for instance, find out whether he really wrote those plays, or whether we could go back to see the pyramids and see them actually under construction. And of course, for most historians, that's a dream. They would love to be able to time travel and go back and see how things really began. Astronomers are unique in that they can actually travel back in time. So the universe is a very vast place. The speed of light is fixed and finite. And so when we look out in space, we're looking back in time. For most of us, when we look at the night sky, the moon is, just over a second away, the sun is 8 and a bit minutes away, and the nearest star is 4 years away in light travel time. But when we look very deep with a powerful telescope like the Hubble Space Telescope, we can truly look back to enormous look-back times. So this slide, which is the first of my talk, is the deepest current image we have of the early universe, taken with the Hubble Space Telescope. You're looking really here at an integration of something like 10 days with the Hubble Space Telescope pointing at one place. And as you were waiting for the lecture to begin, maybe you were wondering, what are the significance of these little triangles, little squares here, with numbers next to them? These are the 7 most distant objects that we currently can see and know exist in the early universe. And we're looking back not a few minutes, not 4 years, but over 13 billion years. So we're looking actually 97% of the way back to the beginning. So this is a glimpse of the universe when it was 3% of its present age. And so we can actually witness the past directly. We can't witness our own past, but we can witness somebody else's past, and we can statistically determine what the universe was like when it was very, very young. So astronomers tend not to use miles or kilometers when they look out in space. These numbers are just too cumbersome. And so we use both look-back time, that is the time that the light ray has taken to reach us, and we use redshift. And I'll introduce redshift a couple of times during my talk. Astronomers like redshift because, as you probably have heard, the universe is expanding. And the light rays from these very early objects are traveling over such an appreciable age of the universe that the universe is actually evolving while those light rays are traveling towards us. And so they share in the expansion of the universe as they come towards us. And the expansion of the universe stretches these light rays out, and the redshift is the amount by which that light is stretched. So that the further away an object is, the earlier in cosmic history we're seeing it, and the greater the redshift, the greater the factor that the universe has expanded since the light left the object. So for instance, here we are today, and if we look back to very, very early times when the universe is only a fraction of its present age, the redshift can be very high. It can be numbers like 3 or 4 or 5. So the light has been stretched by this factor, by the expansion of the universe. If you're up for it, the redshift is the factor by which the universe has expanded since the light left that object. So this is exploration at its most fundamental. It's the frontier, finding the very earliest objects. And it's an adventure that is possible because we have very, very powerful facilities. We have the twin Keck telescopes. This is the reason I moved to Caltech in 1999, was to get my hands on these fabulous telescopes. But a telescope is really only as powerful as the instruments on which we place on that telescope. So what you see here, and I think you'll agree they're pretty formidable instruments considering their size, are spectrographs that are built in university departments, including Caltech, that exploit the light-gathering power of the 10-meter Keck telescopes. The DMOS spectrograph built at the University of California at Santa Cruz is an optical spectrograph. It breaks the light from these galaxies and measures their redshift, and hence places in cosmic time the epoch at which they're observing them. And most recently, a fabulous instrument built here at Caltech in partnership with UCLA, MOSFIRE, which is an infrared spectrograph. And these will feature prominently in my talk. But it's a partnership between the ground-based telescopes and space telescopes. And of course, everybody has heard of the Hubble Space Telescope. It features prominently in my talk. But also Spitzer, operated here in Pasadena. Spitzer Space Telescope is an infrared telescope. And I'll show you the great partnership between these two space telescopes. And for the early part of my talk, the Wilkinson Microwave Anisotropy Probe, a space mission that studies the glow from the Big Bang itself and tells us part of the story of when galaxies may have switched on for the very first time. So the history of the universe in one short swoop is that we believe the universe began with a Big Bang 13.8 billion years ago. The earliest signal that we see is an isotropic glow of that Big Bang. We see the thermal signature from the Big Bang itself in the microwave background. And after the microwave background, the hydrogen atom forms for the first time, but the universe is dark. There are no stars or galaxies. And there's this period, which we call the Dark Ages. And then there is presumably a moment when starlight first switched on. And that's the theme of tonight's talk. Now, I know it's surprising that we understand quite a bit about the glow from the Big Bang, and that's because it's an all-sky signal that has been ruthlessly pursued by many experiments, including many led by Caltech professors. This era of cosmic dawn, when the very first galaxies and stars switched on, has required the painstaking development of powerful facilities, cameras on Hubble, spectrographs on Keck, deep images with the Spitzer Space Telescope. So let me start with this cosmic microwave background. What is it? Well, it is basically the glow from the Big Bang, and it was first seen in 1965 with an experiment in New Jersey. I know it's difficult to imagine making a discovery in New Jersey, but this is actually where this discovery was made. And the Nobel Prize was given to the two experimenters, Penzias and Wilson, who found this isotropic signal across the sky at microwave frequencies. Remember redshift? This is the glow from the Big Bang redshifted by 1100. So the universe has expanded 1100 times, a factor of 1100 times, since this radiation left. And that's why it's shifted from the region where it would be if we could observe it at rest in the ultraviolet and optical out to microwave frequencies. And this is the telescope that was used. Then in 1992, the COBE satellite, for the first time, detected ripples in this signal. In other words, it's not completely smooth. There's structure in it. And these are the seeds of the galaxies that we see today. They are the beginnings of the ripples that come together under gravity and produce the first stars and galaxies. And most recently, the WMAP satellite and a European satellite, the Planck satellite, has given us extraordinarily detailed information on these ripples and how they fit into our understanding of how structure grows in the universe. So what happened next? Well, this glow from the Big Bang basically ends when the hydrogen atom formed. And the hydrogen atom is a proton and an electron, and at 370,000 years after the Big Bang, the hydrogen atom formed for the first time. But there's no starlight. It's just clouds of hydrogen gas. And we call this period the Dark Ages. Astronomers are very good at, mysterious names. We have dark matter, dark energy, dark ages, and this is extraordinarily good for fundraising because, it implies that there's this mystery which, astronomers are still struggling to understand. Now, I told you there were ripples, and these ripples grow under gravity. Gravity is an attractive force. It brings together these clouds of hydrogen gas. These clouds eventually collapse, and as they collapse, they heat up in the middle. And a star is a nuclear furnace. It is converting hydrogen into helium via nuclear fusion. And as the clouds collapse and switch on and shine as starlight. And we'll see that suddenly the universe is bathed in starlight. It would be fabulous to observe this moment. That's really the holy grail of my talk. But also what happens at this moment is that the stars are so luminous and hot that the radiation from these stars breaks apart the hydrogen again. And we call this process reionization. When a hydrogen atom is broken into a proton and electron, it's ionized. Now, it's an unfortunate fact, but we live in a world with theorists, and the theorists are always ahead of the observers, and my favorite theorist is Professor Avi Loeb, who works in the same area that I do, but he's not an observer. And he's at this very minor university on the East Coast, which you may have heard of, called Harvard. And I like this picture very much because it's his Scientific American view of this whole process of cosmic dawn and reionization. So here's the glow from the Big Bang. Here's the dark ages, dark hydrogen clouds. They switch on for the first time, and you see these little stellar cities. And then the hydrogen atom, proton and electron, is split apart again. And so we have these ionized bubbles, which is just full of protons and electrons. And presumably, as time progresses from left to right here, these ionized bubbles become more numerous. They start overlapping. And today, the universe in deep space is completely ionized. And to the extent that Avi Loeb can calculate this in his computer, he tells us that this could occur in any period. Something like this whole process would take somewhere between 200 to 800 million years after the Big Bang. And so if we want to observe galaxies and young stellar systems in this period, when the universe was 5% or less of its present age, we need to go out to redshifts of 6 to 20, which is a really formidable task. Now, I mentioned the WMAP satellite. It was not designed to look for this cosmic dawn. It was designed to study the microwave background, the glow from the Big Bang. But a byproduct of that wonderful satellite is that it discovered that the microwave radiation from the Big Bang is polarized. And the polarization is caused by the electrons that have been freed by the starlight at cosmic dawn. And so by analyzing the polarization signal in the microwave background, one of the most significant things that the WMAP satellite did was to confirm the numerical work that people like Avi Loeb did, that this redshift interval, 6 to 20, corresponding to 200 to 800 million years after the Big Bang, is when this all happened. And that's a pretty big window to search, 200 million years after the Big Bang to 800 million years after the Big Bang. And so my role as an observer is to try to chart this history directly. So I have a movie here, which is another, of course, theoretical movie of this reionization process. So what you see here is a box of space where the dark areas here are neutral gas, hydrogen gas that's in the dark ages. And as time progresses, these stars at the center create these ionized bubbles, which are these blue regions. And I don't know if you watch it closely, these bubbles start to connect with one another like Swiss cheese. And the red areas are the boundaries of the bubbles where the gas is being shock heated. And eventually, as the evolution progresses, the ionized bubbles completely connect, and we're just left with the stars and galaxies which we see today. It's a rather slow movie, but it does, this is representing several hundred million years, so I have sped it up a little bit. So, the great thing about working at the frontier is the questions are so simple, when did the Dark Ages end? And was it a sudden event? If we could take a spaceship there, were all these stars suddenly switch on all at once, or was it a gradual process? And at the most fundamental level, are we absolutely sure that galaxies and stars ionized this hydrogen gas, as in those simulations? What if there's some other process that could be doing it? And perhaps the most exciting thing, can we look back far enough to find the beginning? Can we actually witness this event, find pristine galaxies that are forming stars for the very first time, this moment we call cosmic dawn? So largely here at Caltech, we've made great progress in tracing the history of the universe out to redshifts of about 6 or so. And I just like this slide very much because it just shows we live in an evolving universe. So here are 2 galaxies very close by. So we're observing them more or less at the present age of the universe. This galaxy is what we call an elliptical galaxy. It's really just a ball of stars. The stars all have the same color. Turns out they're pretty well the same age, and they're really quite old stars. And here's a spiral galaxy, very much like our own Milky Way. And you can see it has a nucleus, it has spiral arms, and generally the colors are much bluer because the stars are somewhat younger. Well, these are all Hubble images. If we go to a redshift of 1, which corresponds to about 40% of the way back to the Big Bang, you can see galaxies that look, obviously they're far away, so the detail isn't as good, but you can see that there are these two galaxies resemble this elliptical galaxy. This galaxy looks like a slightly messier version of a spiral galaxy. It's got a nucleus. Maybe the spiral arms aren't completely well developed yet, but one might say that this is an immature version of this galaxy. And then there are irregular galaxies, and it turns out there are somewhat more of those than we do see these irregular galaxies locally, but not with the kind of abundances that we see at this redshift. But if we go to when the universe was only 2 billion years old, so this is about a redshift of 3, you can see the galaxies are very different. There are no spiral galaxies. Many of them are multiple. They appear to be merging, and they're physically very, very small. So what you're seeing in this slide is not the evolution of one object, but what you're seeing is a time slice of the history of the universe as seen through these galaxies. And how do we know that these galaxies are at these particular distances and hence being seen at these slices in cosmic time? So here's our friend redshift again. So as an object is receding, its wavelength gets stretched, the universe is expanding, and so we measure the redshift of these galaxies with these spectrographs on the Keck telescope. Now, one very clever way of pre-screening which galaxies are actually the most distant is a technique of imaging the sky in different filters. And so here's a small area of the sky studied in a red filter, a green filter, and an ultraviolet filter. And you can see some of the galaxies are present in all of the color filters. This particular galaxy is present in the red filter, the green filter, but then it's mysteriously absent in the ultraviolet filter. And that's because the spectrum of this galaxy is being cut at this wavelength by absorption. And we know where this absorption occurs locally at rest in the universe, and so we can estimate the distance and the redshift of this galaxy by this technique. Now, this technique is called a dropout. This galaxy is then called a dropout because it drops out in this particular filter. So one of the first milestones in the use of the Keck telescope was made by one of my colleagues, Chuck Steidel, and he took pictures with the Palomar telescope, and he found all of the galaxies in this very wide area that have this dropout signature. And here they are circled in blue. And then he went to the Keck telescope, and he proved that they were really at these great distances. A redshift 3, corresponding to when the universe was 2 billion years old, so about a seventh of its present age. So this was, like opening the door to the high redshift universe. Now, this technique of using these filters to find distant galaxies has been exploited ever since by many groups, including our own. Steidel was selecting galaxies that dropped out in the ultraviolet filter, but you can select them to drop out in the blue filter, in a visual filter, or in this case, an infrared filter. And as Hubble took deeper and deeper images, so various groups started to exploit this technique to find higher and higher redshift galaxies. So Steidel opened the door when the universe was about 2 billion years old, but we've been pushing out to when the universe was less than 1 billion years old. So here's a galaxy seen in an infrared filter, and then dropping out in this visual filter, corresponding to a redshift of 5 or so. So when I arrived at Caltech, this technique had been proven, and this new spectrograph DEIMOS appeared on the Keck telescope, and we pushed the frontier back to a redshift of 6. So a redshift of 6 is when the universe is only 1 billion years old, so half the age that Steidel's objects were found. And here's a spectrum. This is what spectrum looks like. So here's wavelength. And this particular glowing line of hydrogen is called Lyman alpha, and it's a very important line, as we'll see. And it allows us to measure the redshift of this galaxy, and hence how far away it is, and at what point in cosmic history we're seeing it. So this is basically the frontier in 2003 or so. Now, let me introduce Hubble. So Hubble is orbiting about 350 miles above the Earth. It orbits every 40 minutes. And as Tom mentioned, we apply for observing time once a year, and it's extraordinarily competitive. There are 10 times as many proposals as there is time available. So we spend, several weeks writing our proposals, making sure that every possible question that could be asked of us is answered. And even then, we don't get the observing time sometimes. So here's an image of a small patch of sky observed with Hubble, and this is 13 orbits. So that's about 8 hours of exposure looking in one particular place. Hubble started doing truly extraordinarily deep images in about 2005, and this is called the ultra-deep field. This is an interesting story. First, they had a deep field, and then they decided, let's do it even deeper, so they called it the ultra-deep field. This is 400 orbits, so this is like 10 days of pointing in one patch of sky. And if we just look at, this is the same area of sky, you can see much more detail, obviously, in the deeper image. But of course, by exposing for so long, you uncover truly faint objects that you just couldn't see in the shorter exposures. And so these images have generally been publicly available images, and so they've led to a revolution in pushing back the frontier via this dropout technique. So this shows the number of galaxies that are star-forming selected via this technique. And here we are today, redshift 0, the local universe. And as one goes back in time, the galaxies become more active. And then, as one goes to the very earliest times, the number of galaxies is decreasing. So it looks like we're getting close to a period when there are far fewer galaxies than even in the present-day universe. So you can think of this as a life cycle. This is effectively cosmic dawn out here, somewhere out here. Then galaxies assemble their stars. They become very, very active and shine more brilliantly. And now, sadly, the universe is in decline. We're in the later years of galaxy formation. Galaxies basically are running out of gas to convert into stars. Now, at Keck, our task has been to trace this evolution out to the highest redshifts, redshift 6. And so over a number of years, we've done big surveys with the instruments at Keck. So the DMOS spectrograph, I've told you. Now we're moving to this new infrared spectrograph, MOSFIRE. And this is the number of galaxies that we've studied. I like this slide because this is the European competition, and you can see they just haven't, they really haven't cut it. We have many more galaxies. But this is extraordinarily hard work. So at a redshift of 6 with the DMOS spectrograph, we're spending 2 nights, 2-night exposures, even with the biggest telescope in the world. 8 to 12-hour exposures. And when I was beginning my career in astronomy, one couldn't even take pictures this faint. But now, thanks to technology, we're getting spectra of these objects and proving that they are at these distances. So here's this glowing line of hydrogen again, and the number here represents the redshift. And the spectrum shows this glowing line of hydrogen frequently at this redshift. Now, I think being at Caltech is great fun, largely because we can take our students observing. And, a student at Caltech can actually contemplate doing a thesis, a PhD thesis, on something as fundamental as, when did the Dark Ages end? And, of course, they have to work pretty hard, but this just is a snapshot of some of the students and the stories that go along with them. So this student here is now a professor at Arizona, Dan Stark. He was the guy who took us out to redshift 6, basically. And he got on the front cover of Time magazine, which is pretty amazing. And it's an interesting story. If you read this actual article, he features quite amusingly in it. Here's another student who's just finished, Tucker Jones. He likes to observe in his pajamas, I think. But he's actually at the controls of the 10-meter telescope. So he's actually able to control the telescope and the instruments directly himself. Now, it's not all fun. Occasionally, we get cloudy nights. And that's really disappointing when you think of the investment in an instrument like the Keck telescope. Then, my role is to keep the spirits up for these students. If there are several cloudy nights in a row, we usually get a bottle of wine or something. And I think that's why this photograph is slightly blurred. Anyway. Okay, so let me take you through the remarkable discovery that one of my students, Matt Schenker, has found, which I think is really quite spectacular. And it really relates to when did the Dark Ages end. So I know this is a bit heavy, but this is the atomic energy levels of hydrogen. And the Lyman alpha line, which I showed you here, is actually a hydrogen line that comes from this energy level down to the ground state. And it's an incredibly important line. It's the glow of the hydrogen gas heated by starlight, basically. But this line finds it very hard to propagate out of a galaxy if the galaxy is sitting in the Dark Ages. As this line comes out of the galaxy, it gets scattered many, many times by the hydrogen atoms that are surrounding the galaxy. So in this little cartoon, here's a galaxy, and it's glowing with this hydrogen line, but the line can't penetrate the hydrogen. On the other hand, if the galaxy is in an ionized bubble, remember that movie with the blue ionized bubbles, then this hydrogen line can get out. So the trick is that this line should be easy to see when the universe is ionized, but when we get into the Dark Ages, this line will start to get snuffed out. And I have a little analogy for you to make it easier to understand. You're sitting on the freeway looking back. Every car is a galaxy, and you're looking back in time. Every headlight is a Lyman alpha line of hydrogen. And as you enter the Dark Ages, it's like suddenly hitting a wall of fog. Those headlights just don't penetrate the fog. And so basically, these lights will start to dim and decay. So what Matt has found is that the fraction of galaxies that show this line is very high at a redshift of 6 when the universe is 1 billion years old. It's about 50%. But as you go a little bit further, only a couple of 100 million years, it starts to drop. So here, at redshift 6, 50% of the galaxies show this glowing line, whereas at a redshift of 7, it's like about a seventh, something. So it drops really dramatically. And this, this work is important, I think, because it's telling us that the Dark Ages, we are actually at the threshold of the Dark Ages at this redshift of 7. So back to Hubble. So Hubble got a brand new camera in 2009. And it's an infrared camera, and it's been spectacularly successful in probing even earlier galaxies. So here it is. And here are the astronauts making sure it's just completely 100% watertight. And it was put on the Hubble Space Telescope in May of 2009. And it has better sensitivity than the earlier camera, which itself was quite remarkable. It has smaller pixels, that means sharper images, and it has a bigger field of view. It means it's much better for surveys. And if you place all these three in context, it's something like 40 times better than the previous camera. So here's an image. Remember what an orbit is? An orbit is 40 minutes. Here's 16 orbits with the new camera. And here's 72 orbits with the old camera. So I'll flip between these. So if you just go to, let's see, if you go to this area here, 16 orbits with the new camera. Look at this little faint thing. 72 orbits with the old camera. Clearly fabulously better, much more efficient. And sharper images. If you look at, this double, you can see there's just a blur in the old camera. So one of the first things the director of the Space Telescope Science Institute did when this camera was launched was to go back to that ultra-deep field and say, let's spend 100 orbits exposing in this one area of sky. And he made it clear that the data would be publicly released on a particular date in September. And everybody was waiting for this date in September, and astronomers were actually writing the papers before they even got the data. You know, they wrote papers and left blank spaces for the results. And so, you know, when the results became public, it was actual pandemonium because basically everybody was racing to get the results out ahead of everybody else. And I have to tell you, it's bad news. I really wasn't the first paper. So the papers I were involved in were the red papers, and we were pipped by, I think, 2 or 3 days, I think that's all it was, by our rival colleagues at the University of California at Santa Cruz. But I got my own back, and I'll come back to that in a minute. So here are the papers, 12 scientific articles in 4 months from 4 international teams. So a year ago, we started a new campaign with Hubble, and we decided that we would go back to this ultra-deep field once again. And so through a competitive process, we got another 128 orbits. So that's about 8 days or so, looking again at this field. And this is our team, and here we are at Edinburgh in Scotland, and it's a collaboration between Caltech, Edinburgh, University of Arizona, UCLA, 2 Japanese in Tokyo, Paris, and Space Telescope. And this image is the deepest image that we now have, and I've shown you this before. And we found these 7 objects much further away and at earlier times than before. And they were found with this same dropout technique. Now, let me explain. Before these observations, there was only one object thought to be at these great distances. So what you're looking at here is this dropout signal again. So the filters are now infrared filters. So you see the galaxy, and then it disappears. See the galaxy here. These objects are truly extraordinarily faint. For those of you who have amateur telescopes, these galaxies are 30th magnitude and extraordinarily faint. And I've ordered them here in redshift and also in the age of the universe at the time the light was removed. And the most distant object, which of course the journalists always want to talk about, is somewhat controversial because it's only seen in one filter. And it disappears in all of the other filters. And we can't rule out the possibility that this galaxy is a pathological object which has a strong contribution from an emission line at lower redshift, which is why it has a question mark. But all of these other galaxies have been subsequently confirmed by independent studies. Now, 7 objects at these early times is exciting, but there is another technique which we've been using to find these objects too. And I'd just like to do a little diversion here because it's a very cute method. I probably don't have to introduce this gentleman to you, okay? But he predicted that light does not travel in straight lines over large volumes of space. Light can be deflected by massive objects. And this was one of the predictions of his theory of general relativity. So it's conceivable that in the universe there are massive assemblies of material, clusters of galaxies, which act as giant telephoto lenses that focus the light from galaxies at very great distances. And this is a trick that we call gravitational lensing. It's very much like optics. The lens has to be obviously in between the source and the observer, and it helps if it's about halfway in distance. And the discovery is quite amazing because Einstein predicted this. And of course, the question is how to test it. And the only way you can test it easily is using the sun as the lens at the time of an eclipse. And so Eddington, this brilliant theorist, went and made these measurements of a star cluster at the time of the eclipse and confirmed that this deflection, this very, very small effect in the case of the sun, My wife gave me an Einstein calendar some years ago. You know, every month had a picture of Einstein. There was Einstein at the blackboard, Einstein riding a bicycle. You know, by the time I got to April, I realized he was always wearing the same suit. So here's a movie of gravitational lensing. It's a simulation. What we've done here is take a dark lens, passing it over this ultra-deep field. And what you see is, depending on the degree of alignment between the background objects and the lens, you can get spectacular magnifications. You can also get multiple images. You can see the same source by two different routes through the lens. And the mathematics of gravitational lensing is absolutely fascinating. And it goes back actually to the 60s, but it really hasn't taken off until the Hubble Space Telescope. So pretty soon after I got to Caltech, we found this pair of images here. It's actually a mirage. They're two images of the same galaxy gravitationally lensed by this foreground cluster of galaxies at a redshift of 5.6. And we went to Keck, and sure enough, here's this glowing hydrogen line from these two objects. It's not two objects, it's two images of the same galaxy. It's magnified by a factor of 30. That's fabulously important, isn't it? To have a free telescope in the sky that can boost the signal by a factor of 30 or so. 3 years later, we broke our own record and found this galaxy at a redshift of 6.8. This one is three images of the same object. This one, and this one. And it's magnified by a factor of 25 or so. Well, as often happens, this has become an industry now, and the highest redshift gravitational lensing lens is at a redshift of 10.7 by Dan Coe, who was a postdoc here and is now at Space Telescope Science Institute, and it's three images of the same object. And again, it's seen by using this dropout technique. So this is spectacular. So there are these two techniques. Point Hubble in one area of sky for a long, long time and do a survey, or hitchhike through these clusters. The great thing is that we agree. The number of galaxies that we're seeing when the universe was only 350 million years or so, by these two independent techniques, agrees pretty well. And it's a smooth decline. So there's no, fiscal cliff or anything. We haven't reached the beginning, okay? This is declining really quite smoothly. And it suggests, as we'll see, that there are galaxies even further out there to be discovered with more powerful facilities. Now, you may think, did Richard Ellis really use Hubble for 7 days and only find 7 galaxies? And clearly that's not the case. So if you come back a little bit in time to a lower redshift, Matt Schenker found twice as many galaxies had been previously known, and obviously they were intrinsically fainter than the ones that had been previously known. And they're shown here in color-coded. The ones between 6.3 and 7.2 are blue. The ones between 7.4 and 8.6 are red. And I don't know if you can see, some of them are clustered. See 4 objects here relatively close to each other on the sky. So this is very important because it tells us how many of these galaxies are luminous and how many are intrinsically feeble. And it turns out that this distribution of luminosities, which we've been able to probe much better with this deeper data that we got from Hubble, that the number of feeble galaxies is dominant. So if you went out to these early times, most of the radiation, most of the starlight is in really tiny little, large numbers of little feeble galaxies that are really very, very small and numerous. And these are presumably the building blocks that merge to make the bigger galaxies that we see today. We can also look at the colors of the stars in these galaxies, and that's where all of the filters that we use to great advantage with Hubble allowed us to look at the colors of these galaxies, whether they're genuinely young. Now, a star is, if a star is what we call a first-generation star, it is made of hydrogen and helium only. These are the only elements that are made in the Big Bang, hydrogen and helium. So material that makes up you and me, like carbon, magnesium, silicon, iron, that is only synthesized in the centers of stars. So a first-generation star would only have hydrogen and helium, and it turns out would be very, very hot and extraordinarily blue, and that's shown by this blue line here. But a star that has already got those heavy elements will be less blue, and that's shown by this green line here. So by looking at the colors of these, this large number of galaxies that Matt Schenker found at redshift 7 and 8, and measuring their colors precisely, we could say whether these galaxies contain the first generation of stars or not. And the answer is they don't. These are already galaxies that are 100 million years old. So this reinforces the idea that we haven't yet got to the beginning. We've got to probably probe another 100 million years or so to find the very first generation of galaxies. Now I want to come towards the conclusion of my talk, and I want to now turn to the Spitzer Space Telescope. And I told you that there's a great partnership between Spitzer and Hubble. So what is it? Well, it's truly remarkable that Spitzer is a very modest telescope compared to Hubble. So Hubble is a 2-meter telescope, 2.4 meters. Spitzer is an 85-centimeter telescope. But the crucial thing is Spitzer is working at infrared wavelengths, longer than we can see, wavelengths longer than we can see with Hubble. So here's a galaxy at a redshift of 6, and here are the Hubble detections in blue, and here are the Spitzer detections in red. And Spitzer is sensitive to the old stars that have been shining for a long, long time, whereas Hubble is sensitive to the young stars that are very hot and recently established. So the partnership between these two tells us the contribution that stars have been making over a long period of time compared to the contribution that stars are making very recently. In other words, it gives us the ages of these galaxies. So in this particular experiment, so this is quite a long time ago now, we were able to deduce the age of this galaxy by carefully comparing the Spitzer and Hubble observations. And as Tom Sofer will know, the progress with Spitzer has been just as dramatic as it has been with Hubble. People have spent heroic exposures exposing deep with Spitzer and measuring how the old stars grow in number as the universe gets older and older. And all of this is also pointing to this idea that there's been a lot of star formation at very, very early times. And Spitzer plays a key role in this equation. So we can wrap up the whole story and say probably galaxies did cause this breaking of the hydrogen atom, which we called reionization. We can look at the star formation history with Hubble, and we can reconcile that with the old stars that we see with Spitzer. We can predict that the universe was probably completely dark at a redshift of 15 or so, and became fully ionized at a redshift of 6. And although there's some uncertainty, we can predict the electrons are there to polarize the microwave background. So let me end with the future, which I think is very bright. So we have this expensive but very exciting project called the James Webb Space Telescope. James Webb, a NASA administrator who was very influential in the Apollo lunar mission. This is a segmented mirror telescope that will not orbit the Earth, but will go out to a very remote location, and therefore won't be visited, so better work. And it has a 6.5 meter aperture. It has very lightweight beryllium mirrors that have a gold coating, a very small, thin layer of gold on the mirrors. This will be effectively Hubble's successor in this search for the very early objects. It will move to much longer wavelengths than Hubble, so it will penetrate to earlier times and higher redshift. There are a number of instruments on it. The instruments are more or less complete now. This is a spectrograph called NIRSPEC, Near Infrared Spectrograph. And here's a simulation of a 25-hour exposure on a galaxy of the kind that we're detecting at the limits right now with Hubble. And you can see in this simulation that we would detect oxygen lines. So we would see the composition of the stars in these galaxies. This is something we can't possibly dream of doing at the moment. So obviously we will be able to probe and check when we get to galaxies which have no chemical elements other than hydrogen and helium. So this is a very exciting prospect with the James Webb Space Telescope. And then also in partnership with the James Webb Space Telescope, Caltech's 30-meter telescope. So again, this is a fabulous opportunity. This is a 30-meter telescope, so Keck is a 10-meter telescope. This is a big international partnership. I've been involved in it from the beginning with the University of California, Canada, Japan, China, and India. So really a Pacific Rim telescope sited alongside the Keck telescopes on the summit of Mauna Kea. And really, you could think of the Keck telescope as the forerunner of the 30-meter telescope. Keck was the experimental design for the 30-meter telescope as a segmented mirror telescope. So Keck has these 36 1.8-meter segments. TMT will have 492 1.4-meter segments. And the technology for orchestrating these segments as the telescope moves around the sky has been adequately engineered and tested with the Keck telescope. So much so that our European competitors have adopted this technology for their telescope. Their telescope was originally, of course it had to be bigger. Originally it was called the Overwhelmingly Large Telescope. But then they ran out of money and they de-scoped it, and now it's just called the Extremely Large Telescope. Okay. Now, you could say that TMT could be 20-meter telescope, you know, but we're on track, I think, for construction of this next year as the 30-meter telescope. Now, this is my last slide. One of the exciting things about the 30-meter telescope is that it will have a technology that we call adaptive optics. So adaptive optics is being pioneered, actually, at many places, but particularly at the Keck telescope, and it corrects for the blurring in the Earth's atmosphere. And I don't have time to explain how it works, but basically you shine a laser into the sky and make an artificial star, and the signal from that artificial star is analyzed at high frequencies to map the corrugations that cause the blurring of starlight from the bottom of the Earth's atmosphere. And this is not a pipe dream. This has been working extraordinarily well at Keck, so that we've realized images with Keck that are better than the images with Hubble. Admittedly, the field of view is small, but the sharpness of the images is quite striking. Distant galaxies are very, very small. They are tiny compared to galaxies around us today. And the Webb telescope will not resolve them, whereas the 30-meter telescope will actually break them in, we'll see the structure in those galaxies for the first time. And we will therefore be able to count them and study them much more effectively with the 30-meter telescope than we can with the Webb. The Webb's main advance is that we can go into the infrared and see these characteristic chemical elements. So it will be a partnership again. Hopefully both instruments will be operational together for at least 5 years or so. TMT, of course, has a long lifetime. James Webb probably has a 5 to 10-year lifetime. So I'd like to thank you very much for your attention. Let me end with this gentleman, Edwin Hubble. Very interesting person, of course, a giant in the figure of cosmology, discoverer of the expanding universe, the Hubble sequence of galaxies, and of course the Hubble Space Telescope, therefore named after him. Controversial figure, not very well liked by his colleagues because he had an affected British accent. He went to Oxford as a Rhodes Scholar to study law, then came back and was so enamored by Oxford that he never lost that Oxford accent. But he was a master of words, and he gave a series of lectures at Yale University called the Silliman Lectures in 1932, and he wrote those up in a book which has just been reprinted called The Realm of the Nebulae. And there's a quote in The Realm of the Nebulae that I think just sums up the adventure of studying the edge of the universe. And here it is: at the last dim horizon, we search among ghostly errors of observations. Not sure I like that bit. For landmarks that are scarcely more substantial. The search will continue. The urge is older than history. It will not be oppressed. Thank you very much.